right, welcome to our Wednesday review. Um, I sent out an email or an announcement earlier. So instead of doing a live stream, I'm recording it now and then I'll post it afterwards. So that's out there. I think it's working much better with fewer technical issues. So let's see, where are we? We had our last discussion was on limits involving infinity. And since I wasn't able to live stream, what I've done is I've recorded it, and there is a link to the recorded lecture in this module now. And again, remember there's also resources down here from the online course, so you're always welcome to take a review of any of those. They have quite a few examples worked out, probably more than we can go through. So today, we will look at the review. And basically, I've got two documents there. One was the emails I've been receiving on a few of the questions. Of course, those are for 1.3 and 1.4, so I'm not sure if those are still questions people have, but we'll take a quick look at those as a sort of an overview of what we're doing. And then we have the exam review that's posted in the Math 265 website, web page from ASU. So we'll start looking at that. It's got the questions by section, and then we'll return to it for the last three sections when we get into Chapter 2. We'll do 2.1, 2.2, 2.3. And then we'll do that review day, and then we'll have the exam over what we've started going over. So let me pull up these. So these were questions submitted by students. Actually, I'm going to download it and pull it up in Word. It's easier to write on that way. Okay, it's showing up pretty good. So the question is finding this limit. And what they've asked us to do is remember from 1.3, we're actually sort of guessing at the limit. We're not trying to prove it or algebraically find it, but just either looking at it numerically as it gets close to a point or graphically as it gets close to a point. So their suggestion is, as we're getting close to 3 on either side, see what's happening from these as we get close to, -3. So -3, actually this is from the right side, right? -2.9999. And most of these you'll probably get the answer is if you just get really close. You don't have to do the preliminary ones. You could, but you'll see you'll get closer and closer to the number. The one where we'll pretty much get our answer is right there in the middle. So one way of doing this, and again, what you'll need to do is you'll also need to kind of figure out how your particular graphing calculator works. If you're having struggles, let me know your model. I'll direct you. There's various websites that have videos on how to use them. And I do have experience with the TI-84 and the Casio CG50X or something, or FX or something like that. Going back and forth is a little difficult, but I'd be happy to help you with those. And after this class, I have 2 hours of office hours. So if you have that time available, we could sit down and figure out how to do these things we're doing with decimals in your graphing calculator. So let's go to decimals for this. And we're going to put that equation in, so 5x plus 15 over x squared plus x minus 6. So I like to put in f of x. You could just put y if you wanted to. 5x plus 15. Sometimes you need to kind of put the top in a parentheses, sometimes you don't, but I typically try to do that. And then we have, now that we're in the bottom, x squared, I think it was minus x plus x minus 6. And we're looking at -3. So another thing I might put that's helpful here is that you won't be able to do with the graphing calculator is I'll put in x equals -3 because we're looking as we get close there. So with Desmos, you can kind of put that, what's happening at that point. And then as we come down here and click, we should probably see that at -3, well, there is a value. Okay. But the idea is what is happening as we get close to -3. Looks like we're getting very close to -1. Let's see, maybe we don't. Okay, at -3 it is undefined, which I was expecting. But as we get close, we're getting close to -1 on this side. From the other side, yes, we're getting close to -1 from the other side. So you can just kind of see playing with a trace. The other thing you can do is go to a table of values. In Desmos, you can set that up by adding a table. When you add the table, this is why I use the f of x. I'm going to put in f of x, and I change this from x1 just to x. And now when I put in numbers 2.999, oops, negative 2.999, we see we're getting very close to -1, and you could put in negative 3.00001, getting very close, again, to -1. So that's one way. Any question from 3, we can analyze it with the table. We can analyze it with the graph. We're just looking what's happening to the values as we get very close to a particular x value, which might not exist on the graph, and usually it doesn't. So in this case, it's undefined exactly at x equals -3, but we use those tools. And again, you want to have some practice with doing that with the handheld calculator you have, because on the exam, that's what we'll have you using. If you want to wait a little bit longer, that's fine, but I would, in this next week, definitely start doing it. I personally would use Desmos to get the concepts down, and once those are coming, because it's a lot easier to use, then figure out what features you're using from your calculator, and then focus on that. And again, I'm happy to help you with those. Is that pretty clear about what we're doing in chapter or section 1.3? We're just, again, limits. We're getting close to it and seeing what's happening. Okay, so that was the one question that I got from 1.3. I got a couple questions from 1.4. I think 11 I got 2 questions from. So let's go ahead and take a look at them. In 1.4, we found out a lot of rules and laws and theorems about limits. And so we can apply those things. We don't have to remember what they're called or where they come from so much. Like although one of the questions used the squeeze theorem and it asked you to name it, we're not going to do that on the test. I don't care whether you know it's the squeeze theorem. I care that you know when you're caught between a rock and a hard place. When you've got 2 functions that squeeze you to a value of, say, 2, that function in the middle has to go to 2. Okay. So for this one is evaluate. Now, we've got two kinds of functions here, right? What's the first function? what's the first kind of function? I think I can do it with this. Well, what's the second function? Maybe that's easier to, what kind of function is the second function? Sine theta, a trig function. The first function is just 3 theta, or think of it as 3x. It's a linear equation, right? It's not a big deal. So we've got a linear equation and a trig function. There was some law that said if it's a trig function, maybe we got this later on as far as continuity, but it kind of flows from here that the limit is, we're actually able to evaluate it at that point, and that's what the limit's going to go to. Because both of these functions, their domain is all real numbers. So we can plug in any value for x or y, and it will exist. So we can just evaluate this by saying that the limit is what we get when we evaluate. So we can plug in, notice it wants pi over 2. So we can plug in 3 pi over 2 for theta times sine of pi over 2. Again, there'll be trig functions that come up from time to time. So you're going to want to kind of do a review so that you know what sine of pi over 2 is. Maybe even know what sine of pi over 3 and pi over 4 and pi over 6. Those are the standard ones. But take a little bit of review and say, yeah, those are the standard ones. Pi over 2 is 90 degrees. Sine is going to be 1. Okay. If you didn't remember that, plug it in the calculator. It'll give it to you too. Just make sure when you're using your calculator that, because this is one of those things that I forget oftentimes, when you're doing trig, whether you're in radians or degrees, you'll get different answers. And again, you're in a test, you forget to do that. I've lost so many points because I was, moving forward, stressed out, and I forgot to change the degrees to radians or vice versa. So anyway, let's see, come to the right place. This is 1. What's 3 times pi over 2? Well, it's just 3 pi over 2. So when we multiply these two, this is what the limit's going to be as well, 3 pi over 2. Okay, so take advantage of that in 1.4. We just evaluate it. Don't have to do anything. But sometimes it's, you're just getting into limits. You're thinking you're not quite understanding what a limit is. It's as we get close. You're right, that's at the point when we're evaluating, we're not really using limits, except we're using that theorem that says for certain type of functions, you can just evaluate it and that will be the same as the limit. Okay, so there's ones where, that's all we had to do. Okay. And then this one I had 2 questions on, and I can understand why. So let me, we're going to need a little bit more room. So let me turn that off. Give me another page. Okay, let's come down here. Okay. Okay. Let's turn that back on. So now, we did one of these in class where we had a square root minus a square root, and I just said graph it, and it went to 0. We kind of did it that way. Some of you mentioned doing the, what's that called? The conjugate. Thank you. I blanked out. So the conjugate, which is going to be the same thing with a plus in the middle. And that's really how we have to approach this one, because we don't know what a is. If a was a number, it would probably be easier. We just graph it and probably be able to get to our result. But since a is sort of a constant unknown, we're going to go ahead and work through this. So let's see. I think I'm going to move I usually look to my, oops. Okay, there we go. I work better this way. So what we're going to do, and again, I'm going to drop off the limit for now, but first of all, do you agree with me that we can't just plug in 0 for h, right? Because that would cause division by 0, and it wouldn't give us any value. Let's say maybe going to infinity or something, but we can't do that. It doesn't give us a valid answer. So I'm not going to keep writing the limit because it's just extra work. I know some of my colleagues would say, well, no, that's, You got to keep it. But we're not publishing this. This is our thoughts. Minus square root of 2a all over h. I will do that part. And then we're going to need to multiply the top by the conjugate. And when we do that, then we end up with a difference of squares. So when we multiply it out, the middle term that usually comes when you multiply two binomials is gone. And the radicals are going to be gone. And it'll simplify to something really nice. Okay, so let's change that to red. So we're going to multiply by square root of 2a plus h plus square root of 2a. Now, can we just do that? Good, because that's something. We're multiplying by it, but we can multiply it by 1. So we're going to put it in the denominator, and then we can do this. Okay, we can't just say, oh, let's multiply by anything. If it was an equation, we could do it to both sides, but it's not an equation. So we've got to multiply the top and the bottom by the same thing. And in effect, we are multiplying by the number 1. When we multiply by 1, we don't change anything. So we got to multiply by the same. And this is what makes the complicated part, but we'll deal with it. Let's see, we'll do that. Okay, so we're going to multiply, thinking that everything's sort of in a parentheses. And it's good to, as we go through this, because this technique will work, it's got these two parts. So recognize what the conjugate is, it'll simplify things, and then we're going to have to divide by something, which is not intuitive at all. You're going, where's that coming from? Well, it's because somebody figured it worked, and so we've got to remember that that's what you do for the next step. Okay, so this part's actually, the numerator is very easy because of this being negative and this being positive. The complicated part cancels out, so we don't even have to deal with it. We just have to remember that this is a difference of squares, so really we're just multiplying the first term and the last term, and that's all we have to worry about. We do the cross multiply part, but it will cancel, so let's accept that. And so our new function is going to be, again, the square roots are gone because when you take a square root times a square root, it's squared. So this is just going to be 2a plus h minus, because a minus times a plus is a minus, 2a. Now I'm going to put a parentheses here just because it gives us sometimes ones that has like 2a plus 4, and you've got to remember that that negative is going to distribute to those terms. Oftentimes you just put that negative, you put the new answer, and you forgot to distribute that negative through, and then it makes a mess. Okay, but this case it's not going to be too bad. The denominator gets pretty messy, but we're not going to multiply it out just yet because, well, we're going to see that enough cancels out that the h will actually cancel out. We don't have to distribute it through. So, and again, that's from experience. Sometimes you don't know, okay, I should distribute that h and just do it, and then you basically end up undistributing it. So I'm just going to put a big parenthesis so I don't have to rewrite it, because it's just going to be it's going to be this thing here, right? But I want to multiply out the top, so we're going to get 2a plus 2h. And this just becomes minus 2a over h times the big stuff. So 2a minus 2a, that cancels out, that's 0. And then this is where we can take the h divided by h is 1. So all that's left in the top is the number 2. Beautiful, nice, simple, right? Now we got to deal with that bottom part, and so we will go ahead and write that out. So what we're left with is we've got this 2. Let's see if so we're left with 2 in the top, and then the denominator is the conjugate, square root of, and while I'm at it, again, I'm not sure if I have to or not, but I'm going to distribute the 2 here through to it, 2a plus 2h plus square root of 2a. And now at this time, I'm going to read back and say, okay, where do I go from here? Well, remember, I'm doing a limit. I'm letting h go to 0. So now before I try to get into too much algebra part of it, actually this one ends up being not so bad, can I let h go to 0 now? And the question is, yeah, I can, and the reason I can, because when I plug it in, the whole denominator doesn't go to 0. The only thing that goes to 0 is this part, so I get 2a plus 0. Well, that's okay. It's the square root of 2a. So I go ahead and take this limit by now just plugging it in, 0 for h, because h just disappears. Okay, and so what I'm left with is a 2 in the top. I've got a square root of a, or 2a, sorry. This part became 0. If you wanted to put it, you could say plus 0, and plus square root of 2a. These are like terms now. I can add them together. So 2a, square root of 2a plus square root of 2a, there's 2 of them. So it becomes 2 over 2. Come back here. Switch colors. 2 square root of 2a. I guess the 2 cancels with the 2. I thought it was in there, but did I miss something? I thought I got a slightly different answer last time. Yes. No. We finally gotten it. Usually math, the way we teach math is like 30 years behind. We've had calculators that can calculate very accurately. The reason we used to rationalize is because before graphing or electronic calculators, it was more accurate to actually get it in the numerator because of slide rules and stuff. We don't use slide rules. We haven't used them for actually probably 60 years now. But finally, we've caught up. In the last few years, we say, okay, let's stop with this rationalizing. Although you'll see some textbooks still use it, but yeah, we can leave it as is. Okay, because we've got the technology, we'll handle it. So something's telling me that wasn't quite the right answer because I remember seeing a 2 square root of 2a, or maybe I was looking at the example and I just didn't focus enough. Anyway. If nobody else spots an error along there, that's kind of how to do that one. Okay. There are some other ones you can do the same thing, but it's kind of got an x or an x squared in there. What you've got to do is you've got to divide that out. But all the tricks is when we've got h in the denominator, we're looking for ways that we can get the denominator not to become 0 when we let that h go to 0. Okay. And where this comes from, it's really the difference quotient. And difference quotient is what we're really doing is we're starting with 2 points. One is here and the other's h away. And then what we're doing as we let h go to 0, we're letting the points come together. And you'll see this more clearly as we go forward. And so that gives us the slope at a point, which is the derivative. And then very soon, just like we did with limits, we get all these rules that say, hey, we don't have to do all this technical side. It's just this. And we'll look at some other rules that make taking the derivative much easier. So remember, we're still in the mode of these are the nuts and bolts. This is how, for those in computer science, we're doing kind of machine language programming right now. And then we're going to jump in and say, we don't need that machine language anymore. We'll use something that's a lot easier, that's a click and go forward, So far, so good. So those were the questions I had emailed to me and never answered because part of it is I could send them the answer, but I don't know. It just seems these are ones that we should struggle with a little bit. The other thing is I do get some questions about you put an answer into WebWorks and it doesn't quite get it all. If you can get up into the 90s, somewhere in the 90s on your scores, I'll give you all the points. We're not going to penny, because it does. It's, electronic things can look at it and not get it quite right. Even if it wasn't quite right as the answer, maybe it was the last time it let you answer it, but then you figured it out. I'm going to assume that if you're up in the 90s, you've got good understanding. If you're not quite in the 90s, but you found maybe a lot of errors were causing the problem, let me know. I want the homework as a means to practice and learn. And my feeling is if you're doing that and engaging with it, you should get all the points. We don't want to, the machine didn't say it was right, so I lost a few points here and there. Those all add up. And You know, some of you probably are shooting for that A plus. That's 97%. You don't have much room for losing a few points here or there. So we'll make it work. Okay, keep in touch with me. Any other questions? We'll throw it out to you, and then we'll go to the review. If you. Okay, let me open up WebWorks. And we'll just work them live. Which section? 1.4, which number? 15. Okay. And it's probably the one where we have to, that has another step in there, and that's a good one to take a look at. Again, remember a lot of these, if we can graph it, we can use the graphing. That one, we couldn't graph it. 15, right? Here we go. Now, I'll probably get a slightly different version, but it should have all the something. Was it something like this? Okay, because it's in the denominator. It's not 2 times that thing. Okay, let's go ahead and take a look at that. What I'll do is I'm going to take a snapshot. Oh, I can't do that. Well, I think I just stopped the recording. We'll see. Well, it seems like it's still recording. Okay. Let's just see if we can work it right here. Okay. So let me make it a little bit bigger. There we go. So we want to multiply by the conjugate. So we'll do that. It's going to be 6. Or do we? Let's see. What's that? Yeah, that's what I was thinking. I think in this one, let's try something. Some of these, it's actually better if I hadn't, if I don't know what's the best way to go through this. So we're going to try something. So the other thing, instead of a conjugate, what I'm noticing, I've got 2 fractions. So what I'm going to try is combining them by getting a common denominator. And that probably, as I remember, I think maybe we were working this one in office hours. If I get them to be 1 fraction, then when I flip and multiply, it'll all work out. So we notice the denominator's a plus h on one side and a on the other. So our common denominator is simply a times a plus h. Okay. So how do we get a common denominator? We take each fraction and multiply the top and the bottom by the part that's missing. Okay, so over on this part, the first part, we're going to multiply simply by a over a. Kind of messy, but we'll figure it out. The second one, we're going to multiply by a plus h over a plus h. Okay, and so what that gives us, and we still got the h in the bottom down here, we're going to get 6a, right? That's from these guys over here. And then we get this minus sign, and this is where it's important. Put that parentheses. Oops, I also got, so I get 6a plus h. So I'm going to distribute, maybe I just, instead of doing the parentheses, save myself a little bit. I'm going to take negative 6 times a, that gives me negative 6a, and negative 6 times h, negative 6h. And then in the denominator, I'm sorry, don't really have an h here. In the denominator, I have a times a plus h. Maybe I could distribute that through too. And then that's all over h. Does that make sense? Okay, so I've got common denominator, made them into one fraction. Now I simplify as I go through, and I can see 6a minus 6a, that cancels out. So in the top, all I've got is a minus 6h, which is going to be nice. So now what I'm going to do, I guess I can multiply the... It's going to cancel. I still going to... Okay, yeah, it's going to be okay. So what I'm going to do is I'm going to view the top fraction as one fraction. I'm going to view the bottom part as a fraction is going to be h over 1. And when you divide two fractions, so when you divide a fraction, the second one, you flip and multiply, right? So flip and multiply. So I've got h over 1. When I flip it, what does it become? 1 over h. Okay, so I've got minus 6h over, I'll go ahead and distribute this, a squared plus ah. So that's one fraction. I'm dividing by h over 1, which is the same thing as multiplying by 1 over h. Okay, do you get that part? Because that's kind of, I skipped a step, writing a step anyway. But you've got two fractions. When you divide them, you flip and multiply. And what happens here, see, the hardest part of calculus is not the calculus, it's the arithmetic and the algebra, because you got to just kind of dive in and try different things. So this h cancels with this h. So notice we still have an h in the denominator, and then this just really is 1, right? So that's gone. All we're left with, let me see if I can go up a bit. All we're left with now is negative 6. Actually, let me go ahead and put my limit, remind my limit, as h goes to 0 of negative 6. Remember our signs. And in the denominator, I have a squared plus ah. And again, is it okay now to let h go to 0? Yeah, because then it's just a squared, and the bottom does not go to 0. So it's kind of like each time we're checking, can I let it go to 0? Bad things don't happen, so I don't get division by 0. So I just let it go to 0. 8 times 0, this part goes to 0, but what's left? Negative 6 over 8 squared. And so that's our limit. And that should work. Does that make sense? That help? Okay. So yeah, there's all these little tricky things. Like I was going the wrong way. I said, okay, conjugate works here. Conjugates work really well with the square roots because it gets rid of the square roots. And then we could have used it here, but someone was saying that gets real messy. And sometimes I do that. I wouldn't have known that until I get into it and I go, this is getting messy and it's not getting where I wanted to go. And so half an hour later, I switch and I try, oh, maybe I just combine the fractions. So that's where working through things will help you, because then you'll be prepared as you face different things. You have that experience, you call in that experience. But remember, you don't always do them right the first time. Even if you've been doing it, I've been doing this for 24 years and I get paid for doing it. So I should be pretty good at it, right? But I forget certain things and we do things and there's a lot going on. Other questions? Yes, sir. What's that? 1.2? 1.4? The second one. Okay, yeah, sounds good. So let me just clear that out. I think we are still recording. That's good. And I go back to the problem list. How do you guys like WebWorks? How many of you have used WebWorks before? Is this your first time? A couple of you have done. My first time too. I'm starting to get used to it, but I wish it was a little easier, but don't we all? Probably, it's not bad though, for free. Remember, this was something created nationally. Any university can use it for free. So then all we have to do is we attach a book to it, and that's the $25 you pay. Actually, you don't pay it. You pay it as, well, you pay it. You pay a student course fee, and then you get your textbook for free. So it's, instead of, even back when I was doing it, it was like $200 for a calculus book. Of course, it was good for 3 series, and that was back in the 1980s, and then they were getting where they're $300 and $400 for those series of textbooks. That's ridiculous. Okay. This one, again, it's another one we did, and what would be nice is, one thing if you read through things, if you click on one of the graphs, it does enlarge it. So that's one of the things you're going to need to do so you can see what's going on here, because this is going to be a graphical interpretation of limits. But we're going to have to get a value here, and then we'll increase the other one. It'd be nice if we could do both graphs at the same time. So first, the first, did you have a question on a particular step of this? Which one? Number 2? Okay, so the composition, very good. So what we've got to do here, I got to switch over to this, is for number 2, we want the limit as x goes to 2 from the left. Okay, so that's, you got to see all these little things. So wait, from the, I said the right, but I pointed the wrong direction, from the left. So coming from the negative direction. And what we need to find out, what is g of x as that happens. Then we plug that number into f of x. Yeah, so yeah. So first of all, we need to find what's happening as x goes to positive 2 from the left for g of x. So we're on g of x here. Where's 2? This is 1, 2. So 2's here. So coming, really? Did I get that right? It's 2? Of course, it might be different on you, but yeah. So coming from the left, what's the limit of g of x? Looks like 0 to me. Okay. It's surprising. It's because I was thinking they'd want us to do something over here, but no. We could have taken the limit at 3, but at 2, maybe they do that later. No, they don't. So what we've got now is when we took this limit, we're doing f of 2. Oh, no, f of 0. Sorry, f of 0. The value g as it goes to 2 was going to 0. And so we pull up, now this is maybe where we have to look at this function. So we look at f of x. Come on, there we go. So what's happening to f of x as we get close to 0? Actually, it's kind of like it's no longer a limit, I guess, because the limit was as we got close to 2. We need that for g. But I guess either way we look at it, what's the value? 1, 2. So that should be it. That equals 2. So our limit would be 2. So we applied the limit to the variable part. It says x goes to 2. And then we got a value. Now that, remember, that's a y value. And in composition, basically, we turn it into an x value when we plug it into f. So it's not a variable anymore. It's the number 0 getting plugged into f. And we just read that off the graph. The limit's already been taken care of. Does that help? Good question. Good question. I don't think I went into that much detail before. And then the other ones, you're doing the same thing. Now, when you've got the limit of f of x times g of x, you are taking the limit for both functions because you're plugging that x into both functions. So you've got to see the limits of both, and then you multiply the limits. Or if you want, you could split them apart and then multiply. But yeah, good. And the bottom, or you add them. Good. But that composition, you only really are looking at the limit of the inside function. Yes, sir. Yes. So really, we just took the limit as x goes to 2 from the negative side of g of x, and we're evaluating it sort of this way, and then whatever that is, that's what we plug into f of x, and it becomes. And again, when we get a limit, it's a number now. It's a y value. We make it into an x value. Exactly. So with composition, it's just really one limit. With these other ones, when we're multiplying, we're actually taking the limit twice. Yes, sir. 1 and 4.5. You got it. Wow, time goes by quick. But and again, I want you to. We'll do number 5, but if you look at the practice the PDF with the practice questions. If you go all the way down to the bottom, there are answers to them, so there's a way to check. But it also gives you a way to work through the problems, paper and pencil. You might want to print them out, get that feel for actually taking a test. That's how we'll take it here. Sometimes I get so used to using the computer now, I don't know how to do things on paper and pencil anymore. So it's 1.5. So let's, where do I go? Okay, so I go back here. Like I said, I'm a little slow at some of this. And then which question? Just one. Okay. And what is, and notice that I've got them open till 9/1, which is what? Is that Thursday? So that's because we're reviewing them now. Hopefully you can get them finished up. If you don't email me, due dates are not a big deal for me as long until we get to the test. The test is the big due date. So we'll make it work. But I'm hoping usually I set a due date first and then we can hopefully get through there. Okay, so find points of discontinuity for each of them given, I think we did this one. This one's not a lot of fun, but so first of all, we look at where are we, and again, they give you like 3 points of discontinuity. Doesn't mean there's 3 points. There might only be one. In fact, there might not be any. So one of the things it says, anyone that, if it isn't, you just put an X in there and we're fine. What we want to look at is the denominator, because that's where we would be discontinuous, right? Anywhere the denominator became 0. So we could factor the denominator 16 minus x squared. That's a difference of squares. So is that good? So 4 minus x and 4 plus x, something like that. Let's get this out of the way. And then in the numerator, we've still got x squared plus 16, which does not factor. So I would say positive 4 and negative 4, right? Because what we do is we say 4 minus x equals 0. Solve that. I add x to both sides, and I get 4 equals x. Or the other place would happen when 4 plus x equals 0. Subtract 4 from both sides. I get x equals negative 4. So those are my 2 points of discontinuity, I would think. What I'm going to do is I'm going to graph it to see what they look like, because that's the best way to tell what's happening. I'm expecting maybe to get asymptotes, and one side will go to infinity, one won't. Do we have infinity yet? Or we didn't get infinity until 1.6, right? So I think this one we won't. Let's see what. Oh, yeah, they will allow us to enter infinity or negative infinity if it does that. But again, what I'm going to do is I'm just going to graph this and see what's happening. I also might have a point of discontinuity that's removable. And again, instead of trying to guess what's happening, let's just graph it. And get that out of there. Get this out of there. What was it? It was the parentheses x squared plus 16 divided by 4 minus x and 4 plus x. Or you could put the original in there. You would have seen it anyway. So yeah, we see asymptotes at negative 4 and at 4. Again, if you were stuck, just graph it first and you'll kind of see the values. And what we see, again, to make it maybe a little more clear, let's get that out of the way. I always like to put my asymptotes in there. X equals negative 4. And then you can click on this color thing here. And I wish all graphing calculators would allow you to do this. And you can make it dotted. Okay, there we got that one. And then we'll put in x equals positive 4. And again, graphing calculators usually won't let you do this because these are not functions. I think the Casio will actually let you do that, but we'll make it blue because, okay, so we see our asymptotes here. And so our points are negative 4, positive 4. Negative 4 from the left is going to negative infinity. as we get to negative 4 from the right, it's going to positive infinity. So what does that mean for the limit itself? Doesn't exist. Okay, so we kind of, now that we can see it, we return here. So we have to choose one to put in here. I go from left to right, so I would guess I would say negative 4 is our first point of discontinuity. And then as it goes to that, as x goes to that from the left, we say it's going to go, see left, I forget. It's going down. So I'm coming this way, I'm going down to negative infinity. So I put in negative infinity, infinity, there we go. And then from the other side, it's going towards positive infinity. So I just, INF, there we go. And then we should be able to do the same thing with 4, at positive 4, but at positive 4, where is it going? So positive 4, from the left, it goes to positive infinity. From the right, it goes to negative infinity. They don't ask us about the overall limit, so we're okay there. Oops. And then for this one, we just put in x. I think we could just do it here. I don't know if we have to put it in, and then we can check it. I always go for, why would I leave the site? Answers check, so those are all right. Oh, maybe you have to put x in everything so it knows. So yeah, you just try it and say, okay, but I should have put x's down in the bottom. So I guess we have to go, because it wants something in there. And now we check it again. Now it's all right. And then I would submit it. Yes, sir. Okay. You got a couple minutes, so. And then if you have to leave, you can leave. But and then again, remember, I'm going to have office hours right after this, so we're welcome to come. Which question is it? 11? Let's give it about 2 minutes. The sound will get down and we'll be able to cover it. Thank you. If you want, you can follow me to it. It's an ECA 339, but it's a little tricky to find the first time, and that's where I go right when I finish.
Yeah, no, I just have 2 questions just to finish up.
Okay.
Like, it was like last weekend, Friday, and I'm like just staring at it because it was like the topic limitation learn, and it was like a piecewise function, and the other one said it could be simplified, but my answer was correct, but it wouldn't take the correct answer.
That's the reason why I round up. So we'll take, but yeah, I'd be happy to look at it after we look at this last one. All right. So still got a couple minutes. So I think we can get this one answered for those who are interested. So, and then I'll start answering other questions. Okay. Okay. And because there's a couple of these. So this is a similar one. It's fine. It's continuous. F is defined below, continuous on negative infinity to infinity. So actually, we're looking where would it be continuous. The only thing that would break it up is that point at x equals 3, right? Because the 3 is the place where the pieces change. So this one goes negative infinity to 3, and this other piece goes from 3 to infinity. We need to find a value for c that makes those values the same. Okay? So what we know, sort of a quick way to do this, is we know it's going to happen at x equals 3. So what we want is when we plug in 3 for x, that both of these are equal to each other. So we can just set this up. We're going to plug in 3 for x. So we get 3 squared minus c. And then on the second one, we've got cx plus 7. So we're going to put 3 in for x. So I'll write it as 3c instead of c3. plus 7. We know that these are equal. We're just going to now solve for c. So I'll add c to both sides. So this now becomes 9 equals 4c plus 7. Subtract 7 from both sides, we get 2. 9 minus 7 is 2. It's equal to 4c. Divide by 4, and we got our answer. So that's 1/2. C is, when c is 1/2, then those two, that boundary point is at the same place. And so that would make it continuous because the left side is continuous, the right side is continuous. It's just whenever a piecewise function where the pieces break off aren't always going to be equal. But this case we can move them together. So it's just kind of, we could have graphed it and stuff, but actually there was a c there. We just have to know both sides have to be equal at that place of x equals 3. All right, we good? If you have additional questions, feel free. Again, you can follow me to my office because it's a little hard to find. That's where I go for the next 2 hours. You can also send me emails with questions. I might not get to them until maybe Friday or this weekend, but I can also make video reviews of them. Again, we have some time, and if you need something extended, let me know.